everyone. Welcome to today's Power Corner. I'm your host, Aalyia Shaukat, Editor-in-Chief of Power Electronics News. Today, we'll be speaking with Anuj Jain, Vice President and General Manager of Sensors at Allegro MicroSystems. Welcome, Anuj. How are you doing today?
Hey, Alia, glad to be here and excited to talk about TMR. It's one of my favorite technologies.
It's very cool. So, from what I understand about tunnel magnetoresistance or TMR current sensing, they're like Hall effect sensors in that they convert magnetic field variations into a proportional voltage differential. But instead of sensing how a magnetic field interacts with moving charges via Lorentz force, TMR sensors exploit quantum tunneling between very thin ferromagnetic layers. Can you describe a little bit more about TMR's quantum mechanical phenomenon and how does this translate to real gains?
Yeah, no, great question, Alia. I think, as you said, right, TMR essentially is a transducer which converts magnetic field into voltage. But, and I will talk about it more, but it's one of the best transducers to do so. And, the best way to think about a TMR is that it's a thin film structure which is put on top of the wafers, right? And um, it has three layers in it. One is the free layer, then it has a barrier, insulation barrier, and a fixed layer. And I'm saying them as one layer, but in reality, each of those layers are at least multiple layers built in it, maybe more than 20 layers. And each of those layers are, um, 1 angstrom to, let's say, 100 angstroms. So that's, to put that in perspective, that's 1/10 of a nanometer to few nanometers thick, right?
Right.
So complex structure, um, but the main phenomena behind TMR is that is of quantum tunneling. So that as the magnetic field is applied to the TMR, there's an electron tunneling that happens between the free and the fixed layer that changes the resistance of the TMR, which translates into the voltage when it's biased correctly. And that's what gives TMR the high gain. That is the unique property of TMR. Um, and in terms of just the material that's used, it's a ferromagnetic material, which is very fast to react. So it gives TMR very high bandwidth and speed as well. So overall, we have a transducer, which is maybe one of the highest gain and the fastest transducers that we have in the market.
Mm. That was very interesting. I saw the app note on TMR technology. We were just talking about it earlier. It's a very good technical deep dive. Maybe we could talk about how TMR compares not only to Hall effect sensors, but also to anisotropic magnetoresistance or AMR and giant magnetoresistance or GMR.
Yeah, no. So I think if you look at Hall, right, traditionally Hall is one of the most popular technology. It's been around for decades, right? And a Hall will generate, let's say, microvolts. 10 microvolt of a signal for 1 Gauss of magnetic field applied. But if you look at AMR, that will generate 20 times more signal, right? A GMR will take it up to 50 to 100 times more as compared to Hall. But if you look at a TMR, that will generate 1,000 times more than what the traditional Halls will generate. And that's what makes a TMR a very unique transducer. And the way Allegro is doing it, right? We internally have the technology we have is what we call as XtremeSense TMR. In that particular technology, we are able to generate even more than 1,000 times with respect to a traditional Hall. And if you look at another another key set of differences, Hall, you know, has a bandwidth. Bandwidth is the speed with which the transducer is reacting, right? The state-of-the-art designs on the market will have Hall sensors bandwidth of few hundred kilohertz, a maximum of 1 megahertz. TMR can let you go a lot higher, right? We just released last quarter, we released a 10 megahertz, industry's first 10 megahertz sensor. So that's 10 times more than what a traditional Hall can do. Bandwidth device. it actually recently won an EDN award for us as well as
I
one of
saw that.
the highlight
Congratulations.
products.
Yeah.
Yeah, no, thank you. So, in terms of bandwidth, TMR can be 10 times more than a Hall, right? And then the other key care abouts for me is, especially when you look at automotive kind of applications, is the stability of that transducer across voltage, across temperature and lifetime.
Mm,
And as a rule of thumb, you can say that Hall will vary somewhere between 12 to 15%. A raw Hall native transducer will vary 10 to 12 to 15% across temperature.
okay.
A TMR will vary less than 2%, 3%, right? So it's a 5 times better when it comes to temperature stability. And
Mm,
the fourth key variable for me would be to compare the technologies would be power, right? And with Hall, if you're doing switches and latches, you can do maybe at best micro power designs. With TMR, we can actually push it down to nano power. So
okay. That's a
that's the
lot.
key difference,
Yeah.
which sort of makes TMR, um, you know, one of the best technologies in the market for doing magnetic sensing. And we in Allegro have really embraced it with some of the extreme sense technology we have.
Wonderful. Well, thank you for that. You actually you answered my next question, which was about these stats. Over 1,000 times larger than well, delivering signals 1,000 times larger than Hall effect sensors, 20 times better resolution than AMRs at 5 megahertz is what I read, and an extremely low output voltage gain variation of 40 ppm per degree centigrade and an enhanced signal to noise ratio. Um, uh, Maybe you can, and you have explained this, it's to a large degree already. Can you explain the importance of some of these sensor parameters such as sensitivity, resolution, and linearity, uh, in accordance to how it might impact the application?
Yeah, no, it's a great point, right? So I think the best way to think about resolution, like sensitivity and resolution, are higher the sensitivity. Sensitivity is nothing but the gain, right? Higher the gain of your transducer, the more signal you have, right? And resolution essentially is, you know, the smallest signal that you can decode, right? For whatever application you are using it, right? I will give you one simple example. TMR is used for current sensing, right? So, the smallest resolution of current we can detect that can be very powerful for, like if you're trying to use it for motor control application, right? Especially zero crossing is very important in motor control application. So if you are able to detect really small current variations, you can have a better control scheme. So
Mm,
that's where that high sensitivity, lower noise, high resolution comes in, right? Uh, Bandwidth is another parameter that we talked about that TMR gives you the highest bandwidth, right? 10 times more than Hall. Where bandwidth matters is, if you have systems where, let's say, increasingly gallium nitride and silicon carbide is becoming more and more popular, right? So in those systems, um, you know, these transistors, these wide band gap switches, they switch very fast. They're very efficient, right? People want to use it. But the problem is that if you if you use a traditional Hall-based current sensor, it will take few microseconds to react, right? So but the problem with some of these wide band gap switches is that they have a limited SOA, right? So if a short condition happens, they need something which can turn them off in hundreds of nanoseconds. And that's where, TMR can really come in and help, provide them that, trigger and make sure they're able to protect the system and protect the switches, right?
yeah, yeah.
So that's another example of why bandwidth matters, right? And
The 10
similarly, if
megahertz. Yeah.
exactly right, and we can talk more about it.
Mm,
I think when it comes to silicon carbide and GaN, to
yeah.
to me, and how that plays into sensing,
Mm,
because that's increasingly a trend. But to conclude your question, I would also give you examples of, other thing I talked about was power, right? That TMR can enable you to do nano power applications, right? So Think of any battery operated applications like your AirPods, right? Your headphones, or even one of the applications we are helping our customers with is continuous glucose monitoring, right? You now have patches that go in. That's where if you have a switch, because these switches, they are the ones detecting when the device is getting activated. So they're always on.
Mm.
So if I'm able to reduce that power from microamps to nanoamps, I'm really helping those, those applications extend
Medical
their battery
wearables
life. Exactly.
absolutely
Right.
need long battery life
Exactly.
on the
So
limited coin cell, batteries.
exactly. And so that's where it adds a lot of value. It can help our customers solve problems in a way that can really help end users, have a better experience with the product that they are using.
Okay. Thank you. That was really illuminating. Maybe we could talk about hysteresis. I know that hysteresis and magnetic memory effects are a challenge in all ferromagnetic magnetoresistive sensors. So, how does XtremeSense TMR control or eliminate hysteresis, and how does that compare to AMR and GMR sensor technology?
Yeah, no, that's what makes I think TMR a little unique. And I think it also comes down to how we are, leveraging some of the know-how we have in the company to do TMR, right? Um, so I think to maybe give you a little bit of a context here is a couple of years back, we did this acquisition of Crocus Technologies. They have one of the best TMR technologies in the market. And when it comes down to hysteresis, right, there are two sort of types of TMR sensors. One are angular sensors, and those angular sensors, they always operate in saturation. So the hysteresis is not that big of a deal.
Mm,
But when it comes to linear sensing, right, like you're trying to measure current or you're trying to measure a position of a magnet along a linear axis, right? That's where hysteresis become really key. And this is where we have we a self-stabilized magnetic structure, which is what we call vortex internally, which is able to always come back to its original position as the magnetic field is applied. And hence it results in a very um, low hysteresis
mm.
in those applications. And that's one of the key reasons we are able to use TMR in, some of the current sensing applications, some of the linear 1D sensor kind of applications.
Okay, so it's called Vortex, right?
Yes.
Yeah. Okay. Um, Maybe you were alluding to this earlier, wide bandgap technologies. I understand, GaN and silicon carbide switching speeds can be a problem for conventional sensors. Sorry. How does TMR address this?
Yeah, no, it's a great question, and it's a very, I think if you look at some of the trends in the market, it's a very key question to ask, right? Because if you look at EVs or if you look at data centers, right, um, wide bandgap switches are becoming increasingly popular, right? And these are gallium nitride and silicon carbide switches. And the reason customers like them is because they are very efficient and they switch very fast. The problem or the downside, as I briefly talked about before, was that they have limited safe operating areas.
Mm,
So if a short happens or any overcurrent condition happens in a system which is using gallium nitride based switches, you need to react fast to protect the switch, in turn protect the whole system.
mm,
A Hall based device will react in microseconds, few microseconds, let's say. But a TMR-based device can then, because of the high bandwidth it can have, can react in hundreds of nanoseconds, tens of nanoseconds. And this is where, the 10 megahertz device that we briefly talked about is one of our key releases for this year, uh, this fiscal year. And another key point to keep in mind is that when you're using these GaN and silicon carbide switches, since they switch fast, one of the things customers are looking to do is to increase the system frequency, the frequency at which they're running their systems. You know, the benefit of doing that is it can really help them shrink the magnetics, right? So if you are using it in a EV, if you're able to shrink that magnetics, you can in turn, make the EV lighter, right? By cutting down the weights, make it more compact and then overall reduce the cost, right? So if you make it lighter, if you're able to, reduce the weight, reduce the size and the weight, you can increase the range of EVs, right? So that's what, doing some of the shrinking is buying you. But if you do this, uh, you will have to have a current sensor, which is, let's say, rule of thumb is maybe 5 times faster than this bandwidth you want to run your system frequency at. So if you used to be 100 kilohertz, you can get away with 1 megahertz sensor. But now if you want to increase it to 1 megahertz, you need something which has bandwidth more than 5 megahertz.
Okay.
And that's where some of the high bandwidth products that TMI enables can really come in handy.
Thank you. So the established TMR product portfolio, it covers everything from micro power switches and latches that draw 110 nanoamps to linear and angular position sensors, as you were alluding to, for linear and proximity measurements, to 0 to 50 amp current sensors, all the way to high current sensors above 1000 amps. Are the TMR junctions physically identical across this range? Are you engineering fundamentally different magnetic tunnel junctions or MTJ structures for these different product families?
Yeah, no, it's a great question. And the short answer is, and then I will elaborate, yes, we are absolutely, tailoring and optimizing TMR to specific applications and use cases. And that's sort of what makes some of Allegro's products offering very unique. But I think the best way to think about this is that we have, you know, TMR is a complex advanced magnetic technology, right? But we now have uh, after this acquisition we did with Crocus, we have now people who have done TMR for decades, right? They understand the materials very well. We have the right equipment. We have the right know-how in the company, which is making sure that we are able to, create TMR solutions um, you know, which are very repeatable, very reliable, right? So that's the foundation we have, right? So, with that knowledge and equipment, now we can look into how we are able to provide solutions which are useful for different applications. And that's where what we have done is we leverage that foundation and we're trying to see what are some of the variations we can do to create TMR solutions which can be tailored to different applications. So what we there are few variables that we look into, like the thickness of layers, right? So
Yeah.
or the size of the unit cell that we use, right? That
Okay.
we call it internally a dot. It's like you can think of it as a pillar of a unit element for the TMR. So if you're doing an angular TMR, you need to have you know a wider dot size, but
Mm.
you need to have your layer thickness needs to be thinner. If
Okay.
you're doing a TMR for current sensing, for example, where you need a lot bigger linear range, you need to have a very small dot size, but you need to have a lot thicker layers, right?
Okay.
So, and then another way is, just how do you even connect these dots that I'm talking about, right? Whether you connect them in series, parallel, different layout configuration, you can change your linear range, you can change some of your temperature performance based on how you even connect them. So in summary, right, we are looking at all different variables, right? We're using
Right.
TMR technology that we acquired as a platform, but then we are looking at optimizing these variables
Mm,
to con to create these unique TMR solutions for each of the applications, where we are able to get the most out of that TMR transducer to provide the best possible performance that our customers need.
mm. That's fascinating stuff. Maybe we could talk more about TMR sensors and how they're manufactured. I understand that TMR technology is deposited during back end of line processing. And what are the main benefits of this compared to front end of line processing methods often used for Hall effect sensors?
Yeah, so if you look at what front of the line and back of the line means, just to clarify, is right. Back of the line is when when your wafer, when the base layers are made and you're doing it towards the end, and front of the line is when you're trying to do that within the base layers of the wafer. So the main benefit of doing back end of the line integration is that now we can, it provides us the ease of integration even on our existing processes and technologies we have, right? So if you have something that you can put on top of the wafer at the back end, then you can use your existing wafer and process and put it on top of it, as compared to if it was something which is more fundamental and has to be done in the front end, you have to completely change your process, right?
Okay.
So what, being TMR, given it's deposited on top of the wafer, and it's something which is very tough to do. It's very precise, so you need a lot of expertise to do it. But since it's done on top of the wafer at back of the line, it enables us to use the custom precision processes that we already have in Allegro and
Mm,
put TMR on top of it.
okay.
See, we are leaders in magnetic sensing, right? So we have a lot of this precision capability, right, in our process and in our designs. And having TMR back of the line enables us to integrate TMR on top of those custom precision grade zero automotive qualified processes that we already have. So we can now add TMR capability, but reuse some of the same old advantages that we had, right? So that's the main advantage.
Yeah.
And I think there's some other key ones. The other key things to maybe talk about is if it's back of the line, you can actually put TMR on top of your die active circuits.
Mhm.
So you don't have to, that lets it be more area optimized integration as well. So those are maybe some of the benefits which, TMR, the, since it's back of the line, right, it enables us to do when we are trying to integrate TMR into silicon.
Wow. So a lot more integration. Um, so, what were the most significant challenges or obstacles to overcome in getting TMR to work on 200 millimeter silicon wafers? And do these challenges impact cost and yield?
Yeah. So there are only few companies which do TMR, so it's not a easy thing to do, right? Like if you compare Hall versus TMR, you will have lots of companies doing it, but they only select few who can do TMR. So it's
Mm,
a fairly advanced magnetic technology,
mm,
right? And we talked about that TMR, in TMR you are depositing thin film over the wafer, right?
mm,
And each of those, and it's not just one layer, right? There are multiple layers. You can have like 20 to 30 layers that are deposited of ferromagnetic material. And
mm,
these layers, as we briefly talked about, right, start of this discussion, are, somewhere between 1/10 of a nanometer to few nanometers
yeah.
thick, right? So, and to
Angstroms.
do it, yes, so
Yeah.
it's like 1 angstrom to 100
Yeah.
angstrom, right? And few, so it's like 0.1 nanometer to 10 nanometers.
Mm,
And to do that over entire wafer and to do it uniformly is a challenge, but it's a challenge that we have mastered,
mm,
and we are able to do it reliably across thousands and thousands of wafer that we are able to produce. And that's just one part of the challenge. And then if to create that unit cell that I'm talking about,
yeah.
you're talking about geometries which are in some cases as big as 5 micron, that's the big,
Yeah.
but as small as less than 1 micron or even zero point
Okay.
0.5 micron. So
Okay.
it requires a very special kind of etching.
Mm.
And that's where, some of the XtremeSense TMR technology we have is one of the very key differentiations that we have. And it enables us to do this in a very reliable fashion and do it at an automotive grade quality, right? That we can create millions, if not billions of units with very low ppm.
Right. Because you're building it on top of, in some cases, on top of those automotive grade processors, so they have to be automotive qualified, right? Okay.
Exactly. Right.
Yeah.
So our DNA as a company is automotive, right? So we are, when it comes to EV or ADAS, these are some of the applications that we play big into, right? And we are very well-known name in automotive. So the products that we are working on, we have to make sure that they are automotive grade. In fact, not only automotive grade, I would say a lot of our sensors are automotive grade zero,
Yeah.
as well as, in terms of just reliability and safety, we have a lot of products which are even ASIL-C, ASIL-D rated in the system,
Okay.
right? So
Okay.
that's very important for us to
Yeah.
make sure that whatever technology we are bringing in is able to meet that automotive reliability
Safety.
and safety
Yeah.
standards.
Gotcha. Um, so there are a handful of TMR sensor manufacturers on the market. You talked about this. So how does Allegro differentiate itself?
Yeah, no, so I think the best way, Alia, is to sort of, to answer this question, I would say it's along three dimensions. One is, we have, right, especially after the Crocus acquisition that I talked about, right,
Yeah.
we now have um, people who have worked, who not only have their PhDs on it, but have worked on decades on, creating TMR.
Mm.
Right? We have these precision equipments, right, which can do all these things that I was talking about, right? You are depositing these extremely thin layers, 20, 30 of those, and then doing very fine geometries with it. So
The etching.
we have this equipments that can do it. We even have now modeling softwares, right, that we can use to predict what performance we'll get if as you're trying to tweak the stack, right? Like we talked about, there are multiple variables that we can tweak to optimize the TMR solution. So in short, right, one of the key differentiation is that we have now the expertise and the capability to do very tailored and unique TMR designs for applications. So that's one. The second is that we are maybe the only company, right, or at least to best of my knowledge, one of the only companies who can monolithically integrate TMR
Yeah.
into a BiCMOS process, right?
Okay. Yeah.
So now think of what advantage it gives us, right? Now you can not only, instead of doing a multi-chip module, now you're putting them all together. Of course, it gives you size and cost advantage, but
Mm.
it also gives us performance advantage, right? That's the reason we are able to go to 10 megahertz, right, for the current sensor we were talking about,
Mm.
because you no longer are limited by some of the parasitics that comes in if you're trying to bond two dies, right, from one to the other. So so that monolithic integration is a unique differentiation. And I think since talking about process, to me, it's very important to also talk about that in Allegro, we have our own, we don't use just a vanilla process out of any fab, right? We have our own proprietary processes with precision components,
Yeah.
which are the reason we are the leaders in the market, right? So now we can marry TMR with that precision process, right? And that gives us a very unique advantage. And I think we might be the only company of very, very few companies which will be running TMR across multiple fabs. So that's
Okay.
another key advantage for us, right? So that's from a process perspective. The third to me is, if you take any TMR, making it is one thing, right? But then you have to what is called as pinning. You have to pin the fixed layer, and that itself is a very custom tailored process. And then you have to test the TMR as well as trim it in some cases, right? And we have decades of experience doing that for magnetic sensors. So
Mm,
now we're bringing all that knowledge and using it with TMR.
mm,
So I would summarize it as saying, I would summarize it as we are maybe, uh, you know, only company or one of very few companies who can do an end-to-end development, integration, and productization of TMR very reliably for all different applications, going from industrial to automotive safety critical applications.
that was a very succinct. That was a very good summary of what you just explained. That was a good sentence. So I think this will probably be one of my last questions. The Hall effect sensor market is quite dominant, standing at $3.4 billion today, and it's projected to increase to $11 billion by 2035, according to SNS Insider. And I know that some of Allegro's literature also suggests that Hall effect sensing tech will lead the majority through 2030. What does the adoption of TMR look like in this market?
Yeah, so I think earlier the best way to think about it is, there's some unique, um, trends that are happening in the market today, right? On the automotive side, you have EVs, which are increasingly, is increasingly getting adopted, right, across all different continents and countries. And also, you have automated driving, right? ADAS systems are becoming more and more popular. TMR is is uniquely suited for us to go after some of these automotive applications, right? Like when it comes to EVs, it has onboard chargers, DC-DCs, right? That's where some of the current sensors that I talked about, right? The high bandwidth current sensors, they can be really useful, right? It's the same, people are trying to use wide band gaps at switches. They're trying to run systems faster in frequency. You need high bandwidth current sensor, right? When it comes to ADAS steering, right? What is the biggest need in steering? It's to get to have the best steering feel when you're driving the car, right? That's where you need the resolution. And TMR, as we talked about, gives you the highest resolution, right? So angle sensors based on TMR can be key for us to grow our ADAS business. And I think that's on the automotive side. But if you look at some of the same technology and same key care abouts, they are increasingly becoming important in key applications like data centers and even robotics and humanoids. So to put that in perspective, data centers, right? If you look at data center power supplies, especially with all the AI boom coming in, the biggest ask is how can I deliver the highest compute power in the smallest area, right? Because they're trying to pack more and more. So that's where, again, they want to have small size and efficiency. They're going towards silicon carbide and GaN, very similar to what's happening in automotive world, but slightly different reasons.
Yeah.
Uh, they That's where our TMR sensor becomes important. They're trying to shrink power supply size down. Again, as we talked about, high bandwidth current sensor becomes important. And if you look at robotics, right, and humanoids, you know, the if you look at one of the most complex structure in a humanoid is the hand, right? And if you think of a hand, right, you have multiple joints here, right? You have your knuckle joint, you're moving your fingers, you're bending your fingers.
Yeah.
All of these are motors,
Yeah.
but you need a position feedback for these motors, and you need something which is um, very high resolution and very small area. And that's where some of the TMR 2D angle sensors that I talked about can be key, which you can argue, oh, you're doing something similar for EPS steering. Yes, but that similar technology, but in a different form factor, can be applied to some of these robotics designs as well, right? So I think the best way to think about it is that TMR, with some of the new market trends, TMR is really enabling us to go after some of these focus applications that we have in Allegro.
Yeah.
And and then also TMR can help us open some of the new markets, right? Like we can go after CT replacement, right? So CTs are key for high bandwidth systems in clean energy, some in automotive. So we can go after those. We can go after more shunt replacement if we can do a very high resolution, small current sensors. So those are new areas or
Mhm.
markets that we can explore leveraging TMR.
Thank you. Um, Final question. Where does TMR go next? So, are there any breakthroughs that Allegro's working on for TMR?
I think the short answer is it's going to go everywhere. But
Yeah.
I think, yeah, but I think you can think of it this way, right? It's going to be just the advantage that we talked about, right? With TMR, it's going to be a very key focus and investment area for us. You will see a lot more products coming out from Allegro, which will be TMR based. And these products will not be just regular products. They will be products which will be, leadership products, which will be fundamentally helping our customers solve problems, like the 10 megahertz current sensor that came out last quarter.
Yeah. Yeah.
So you will see more leadership, more industry first innovative devices coming out that way. And as I go forward, right, I think Allegro's focus areas are, XCV and ADAS on automotive, and then data center and robotics.
Okay.
TMR will become a very key part of our strategy as we try to bring in differentiated products to market for these applications.
Thank you so much, Anuj. This was a fascinating conversation. I really enjoyed it. Thank you very much for your time.
Yeah, no, Alia, thank you. And just to summarize it again,
Yeah.
right? TMR is a key technology, right? So it's a fascinating technology. And I think the way we are doing TMR and Lego with our XtremeSense TMR technology, I can say without a shadow of doubt that it's uh, we are one of the best when it comes to developing, integrating, and productizing TMR. So I'm really excited about leveraging this technology and trying to see what all we can do in robotics, data center,
Yeah.
EVs, and ADAS applications that we just talked about. So
Yeah. It's a lot of applications. I'm sure a lot of applications are going to crop up as well as you were saying. I
mm,
really, really appreciate your time. This was very insightful discussion about TMR.
yeah, no, thank you, and thank you for giving me the opportunity. Love the conversation.
Likewise. Thank you.
Thank you.